Hello, this is Dan Alford with ARC Specialties. Thanks for attending today. This is the first in our series of the ARC University. We're going to talk today about plasma welding. I've found that some of the colleges here in Texas are actually using our videos for training the students, and I was quite flattered by this, so we thought we'd make it a bit more formal. So our first session will be on plasma. It's an underutilized welding process. It's extremely useful, but it's misunderstood. And I feel like if we get this information out, people will embrace the technology and they'll solve a lot of problems. So today's curriculum is going to be fairly simple. We're going to talk about plasma, transferred arc history, that's PTA. We're going to talk about the differences between GTA, which is TIG, and plasma. We're going to talk about the advantages and disadvantages. We're going to show you some applications on joining and overlay. We're going to talk a bit about control theory, analog and digital control, closed loop versus open loop. We're going to talk about the starting and stopping sequences for plasma welding. We're going to talk about error monitoring and torch height control. What we're going to focus today on are welding variables, because that's what we do best. And you have to control and understand each of these variables in order to be able to control the process. We're going to discuss amperage, voltage, travel speed, powder or wire feed rates. We're going to talk about plasma, shield, and powder gas flow rates, because there's three of them. We're going to talk about torch height and its control, about anode size, gas composition, pulse waveforms, and then the oscillation variables. If you can control all of these things, you can make good plasma welds. So let's talk a little bit about the history of plasma welding. Plasma is actually the fourth state of matter. There's solid, liquid, gas, and then plasma. And plasma is ionized gas. And for our purposes, it's an extremely useful heat source for industrial applications. It was invented in 1957 by a fellow named Robert Gage, and it was based upon TIG welding. And it's used in America today for cutting, joining, overlay, and thermal spray. Since plasma is based on the gas tungsten arc welding process, we're going to do a bit of a refresher on gas tungsten arc first. With gas tungsten arc welding, you use a non-consumable tungsten electrode, so that's what we're starting with. There's two types of welding processes, transferred arc and non-transferred arc. Plasma and gas tungsten arc welding are both transferred arc processes, which means you have to have a conductive workpiece for the arc to be conducted from the electrode to the workpiece. So in this drawing, we have a conductive workpiece. With both plasma and gas tungsten arc welding, we need something to shield the hot puddle from the atmosphere. So it's typically an inert gas. The term TIG stands for tungsten inert gas. Plasma is the same thing. We have to have argon, helium, or some combination of gases. And to conduct these gases to the workpiece, we use a collet and a gas lens. Over the collet and the gas lens, we have a gas cup. This is typically with TIG a non-conductive ceramic material to locate and guide the gas to the workpiece. So now we have the torch schematic, we have the conductive workpiece, and I'm showing you a power supply in here. The workpiece is positive, the tungsten is negative, and we have an inert gas supply supplying gas to the torch. If we're making autogenous welds, which means we simply melt two pieces together, you don't need a source of filler materials, but frequently you need some additional filler materials. So what we've drawn in here is a wire feeder to feed wire into the weld puddle. In the welding business, productivity is measured in pounds per hour. So if we can add additional wire into the puddle, we increase the deposition rate, we increase the pounds per hour. One way to do this without increasing the heat input to the weld is a hot wire technique. This is something that has been invented many years ago, and it doesn't complicate the systems too much, but it drastically improves deposition rate, it improves dilution, it's all around beneficial. So what we've drawn is a second power supply, and this preheats the wire as it flows into the puddle, which increases productivity of the welder. With the hot wire welding technique, you actually have to have the wire impinge in the weld puddle. And so what we've drawn here is the tungsten leading the wire. So we're trailing the tungsten with the feed wire, and it actually goes into the puddle, and it has to do this to conduct the energy from the hot wire power supply to preheat the wire. So this is one of the limitations of hot wire. You always have to trail the torch with the wire. So what are the advantages of hot wire? Increased deposition rate. We've been able to hit numbers on the order of 18 pounds per hour deposition rate. Decreased dilution. This is particularly important when you're doing overlays and you're trying to put a dissimilar material on top of one, and you want to minimize the amount of alloy pickup from the base material. And you'd like to reduce heat input because high heat input's seldom good. All these things occur when you use hot wire. But there are always disadvantages. So The one disadvantage is you have to have the wire trailing the arc. It always has to come in behind. That's where the puddle is largest. There's always exception to the rules, but the easiest way to do this is to hit the puddle behind the arc because it's molten at that point. So we're feeding the wire in directly into the back. Another possible problem is if you don't have a gas shield around your wire, and frequently on tight small bore machines you don't have room for gas shielding, and you preheat the wire up to oxidation temperatures, you can actually oxidize the wire and create some problems. The compromise on this is you simply run lower wire currents. We preheat the wire, but not to the point we create any oxidation issues. And then you have the additional cost of the welding power supply as well as the hot wire torch. So that was your refresher on TIG welding with a little hot wire added in. So let's talk about plasma now. Same thing, we start out with a non-consumable tungsten electrode. And you have a conductive workpiece because we're conducting the arc between the tungsten electrode and the conductive workpiece. So again, we have to have a collet to conduct the electricity from the welding power supply into the electrode, much like a TIG welder. Now we're getting down to the differences between TIG and plasma, and it's all in the constricting nozzle or the anode. The function of this is to shape the arc column. Instead of a diverging arc which spreads out, we get a nice columnar arc. So the current density remains the same, it protects the tungsten, and this is where the benefits of plasma lie. Here's another difference. Rather than a single shielding gas which shields the arc, we now have two. We have a plasma gas which flows around the tungsten electrode, and then we have a secondary shielding gas. These could potentially be the same gases, maybe argon, maybe helium, maybe some combination. But what it allows us to do is optimize the gas for each of its purposes. Here's another difference between TIG and plasma. It's the pilot arc power supply. The pilot arc power supply is a small power supply. It's almost always DC, and it's connected between the tungsten electrode and the anode or the constricting nozzle. So we actually have an internal arc. This is a non-conducted arc. It doesn't actually go to the workpiece. This is the pilot arc that stays on, typically on systems, as long as the system is running. This stabilizes the arc. It also improves starting. And in some cases, it's actually contributing to the total heat input of the weld. So here's a photograph of an actual pilot arc, and you see that it's just extending out of the torch. We're using the shielding gas to actually blow that plasma, the fourth state of matter, past the arc impingement point and out of the torch. And so what we have is a column of ionized gas. And since it's already ionized, it conducts electricity. And so if this column of ionized gas or this pilot arc is in contact with the workpiece, you're ensured good arc starting. One of the benefits of plasma is the use of the pilot arc. There are actually two power supplies that operate on a plasma system. So I've already shown the pilot arc on the right in blue, but on the left is the main arc. Now the main arc is between the tungsten electrode and the workpiece. This is what does all the work. So I'm showing that small pilot arc inside the torch, which is between the tungsten and the anode or the constricting nozzle, and then the main arc, which is doing all the work, which is between the main tungsten electrode and the workpiece. It's a combination of these two arcs and these two power supplies that make plasma. So let's talk about why we go to all this additional trouble of the constricting anode and the pilot arc power supply. And it's all about the shape of the arc. So this schematic kind of shows you what we're trying to accomplish here. On the left side of the screen, that's a typical TIG arc. So when the arc leaves the tip of the tungsten, it diverges in a conical pattern. That means as it gets further away from the torch, the arc spot's bigger. So you can imagine if you crowd the torch, if you lower the torch towards the workpiece, then that current density, the amperage per square inch would go up because the size of the spot gets smaller. But on the plasma, it's much more tolerant of height variations. We have a nice stiff column arc which looks more like a laser beam. Okay, what's the advantage of this? Well, it's stiff, so it won't tend to move to the wrong part. It goes where you point it. That's one big deal. The second thing is you've got much higher current density. So we have many more amps per square inch in a plasma column. And so we can use less amps overall and simply focus that power directly where we need it. And it's all due to the constricting anode. So we're going to talk about several different variations of how you can employ plasma. And the first and the simplest is autogenous welding. Autogenous means no filler material. We're simply melting two pieces together. This is used frequently for thin materials, for corner joints, lap joints, things like that. but you have to have sufficient material in your joint to simply bridge the joint and weld it together. Very simple process since you're not adding any wire. The fact that we have the plasma arc concentrates that energy directly on the joint, and this has a lot of applications in the world. But frequently, in my world, you need to add filler material. So one way to do this is with a wire feeder. And so we've got the schematic showing here where we're adding wire into the puddle. Since I don't have a hot wire on this yet, you can feed this in from the back, the side, or the front, but you're reduced on your deposition rates. But this is a good technique if you need to have a joint that needs to be filled with additional filler material, or you want to change the chemistry of your weld joint. Of course, as we mentioned on TIG earlier, you can add a hot wire power supply to your wire feed system and then preheat the wire as it's flowing into the puddle, increasing deposition rate and your productivity. So I've got an example of that. This is a bore torch, which is plasma, but it uses hot wire to increase the deposition rate. So here we have an arc video of a hot wire bore torch using plasma. And what you're seeing, that pulsing is the current pulse, so that's the waveform we're going to discuss later. You can see the wire feeding in from behind the puddle, and so you're seeing the weld come out from behind the torch. This is in the 2G position. We're welding up a wall, and the wire is preheated with a hot wire power supply, and we're capitalizing on that collimated arc that you get with a plasma. It's an interesting variation on hot wire bore cladding. It hasn't caught on yet, but I suspect that the advantages of plasma over TIG eventually will cause people to go to more and more plasma for bore cladding. So with TIG, you're limited to either autogenous welding or wire feed welding, either hot or cold wire, but you can't use a powder because the tungsten electrode is exposed and the powder tends to contaminate the electrode and causing you to stop and have to regrind. This is one of the biggest advantages to plasma. So you can see here on the drawing, what we've done is we've added a couple of powder ports through the anode, and so now we're able to feed powdered materials directly into the puddle. This is a huge advantage. It allows us to use materials which can't be made into a wire. And by that I mean something that's too brittle to make into a wire, or something that has too high a carbide percentage to be made into a wire, or something which simply doesn't exist in wire form. You can create your own alloys on the fly by blending powdered filler materials. So this really opens up a whole lot of possibilities, and it's one of the major reasons that we're running plasma today. So I've actually got a plasma torch here, and we're going to take it apart and show you how it goes together. So here we have a plasma torch. This is an Excalibur designed by Rod Weber, one of my favorite torches. And I'll show you all the pieces. This piece is how you adjust the tungsten. You loosen this to loosen the collet. Here you see the two powder ports where the powder flows into the torch. Here is the main arc power supply. Here's the pilot arc power supply. We have 3 different gas flows, and we have water cooling through the whole thing. Very busy torch. But what I've been describing to you before now is this end of the working end of the torch. So what you see right here is the gas cup. This is what conducts the shielding gas into the workpiece. We'll take it off so we can see what's inside. And if you shake it out, we have a gas lens. This gas lens diffuses the gas into the gas cup and gives us better gas flow. Now inside the torch, this is where the action is. This is the constricting nozzle, or the anode. Let's take it off. You can see it's made of tungsten, it's made of copper, because it is second half of the circuit for the pilot arc. So here we have the hole in the center is the anode diameter, and this is the diameter of the plasma column that comes out of the torch. The 2 holes on the side are for powder. The whole thing's made out of copper because the pilot arc is conducted between the tungsten and the anode, and the main arc is between the tungsten and the workpiece. This whole thing is water cooled right down to this surface. There's a tremendous amount of heat involved here. We have O-rings in here. So you can see the cost of these torches is high, and they're very complex, and you can imagine there are maintenance issues to be done. But it's well worth it if you have the right application for this. So we'll reassemble this torch. Plasma powder feed torch. So I've mentioned some of these advantages, but let's go over them again. You have a high current density. That means the tungsten arc does not diverge. It remains concentrated, more like a laser beam. You have a stiff arc, and don't underestimate the need for this. When you're trying to weld, particularly into a corner, you don't want the arc to jump to the closer part. And so with a stiff plasma arc, it will force that arc into the corner and fuse the 2 points together. The columnar arc is better than a diverging arc. The shrouded electrode is huge. On TIG welding, one of the most frequent causes of stoppages is the tungsten becomes degraded, contaminated either with wire or oxides or whatever, and this forces you to stop, grind the tungsten again. Happens much less frequently when the tungsten is shrouded inside the anode. And this whole idea of being able to powder feed expands your list of weldable materials, and you have much superior arc starting because you have that pilot arc and that ionized column of gas coming out of the torch. If you can get that to touch the piece, I guarantee you'll have an arc strike. With advantages, there's always disadvantages. There's higher torch cost. A TIG torch can be had for $100. Plasma torches typically are thousands of dollars. Increased maintenance, there's a lot going on in a plasma torch, a lot of seals, water flow and such, and all this has to be maintained. You have bulkier torches. Typically, you have a torch which is much larger in diameter. The exception proves the rule. We have some that go down to 3/8 of an inch in diameter, but overall, most plasma torches are larger than TIG torches. And finally, it requires 2 arc welding power supplies, one for the pilot arc and one for the main arc, and each of these adds cost to your system. So this is a video of an overlay weld. What you're seeing here is the part's not moving, but the camera is actually mounted on the torch, and you can see that the torch is oscillating back and forth between the walls of this narrow groove. And if you look closely, you'll see columns of powder coming in from the left and right. What we're putting down is a high cobalt alloy. This is about 58 Rockwell C. What's interesting about plasma is you can actually produce crack-free welds on these high cobalt, high hardness alloys without preheat. My suspicion is that you're not chilling the puddle with a cold wire or rod and you avoid that shock. So you're actually able to create crack-free welds, which you wouldn't have been able to do with TIG. So this is typical of a good application. This is a rock bit for the oil patch industry, and we're applying a journal bearing material for a metal on metal application. I'm going to show you some applications that we've done with plasma welding just to show you the range of parts that you can weld with it. This is kind of the lower limit. This is a 3/1000th of an inch. So this diaphragm on top of this heavy part is about as thick as a human hair. And we're welding it to a piece that's a 1/4 inch thick. It's a perfect TIG job because we want a concentrated arc right on that corner to fuse that thin diaphragm, which actually made of tantalum, to the base metal, which is typically stainless. So that's a very small weld right there on the corner. Keyhole welding. This is another unique thing about plasma. As you're familiar with, plasma cutting is commonly used in industry. And the only difference between plasma cutting and welding is gas velocity. So if you were to turn up that plasma gas flow rate to a point, it will actually cut. And so that you've created a cutting torch. Well, we've capitalized on this phenomenon by controlling that plasma gas flow rate while we're making square butt welds. So keyhole welding allows you to weld square butts up to, I would say, 5/16, maybe 3/8 of an inch thick without any bevel at all. But we have to cut all the way through the part in order to refuse it behind the torch. And so by increasing that plasma flow rate, we'll punch all the way through the part and create a keyhole, as the name would imply. And it goes all the way through the part. So this one here that you see is just a seamer. It's a simple machine. It shows a wire feeder, but we actually keyhole the first pass all the way through the part, and we're punching all the way through a 1/4 inch piece of titanium, very reactive metal. And then the keyhole is formed as we increase the gas flow rate. And then behind the torch, the keyhole heals and we create a solid weld. It's a little bit low, so we go back in with a second pass with some wire, but it's an amazing process. So rather than creating a V-butt weld, we simply weld a square butt joint with no V at all. It's a great process, but before you go out and change all your joints to keyhole welding, you must understand you need perfect joints. You can't have any gaps and such. So keyhole, although it's a wonderful process that works well on ferrous materials, nickel materials, titanium and such, it requires extremely good joints. So here's some photos of that exact weld we just made. The one on the left is the root on the back side of the weld. It's perfect. And that was produced with the keyhole process. We punched all the way through. We melted both sides of the joint, and then it fused behind the torch, creating that perfect root joint. On the front, On the right side, you see the top of the weld, and you see it standing up a bit above the surface. That's because we used filler wire to increase the weld volume as we're making the second pass. Wonderful solution to titanium welding. Since titanium is a high value item, they're willing to spend the time to give me the good joints that are necessary for keyhole welding. But if you'll produce these good joints, you can weld much more efficiently because we have zero groove volume. If you want 100% penetration all the way through a part, you're limited to two techniques. You can either keyhole weld, like I showed you just before, or you can melt in. And so this was a melt-in technique. So we're welding up turbine ducts for stationary turbines, and rather than keyhole them, we're melting through. So this is a little more like what you would do with a TIG, but again, there's an advantage with plasma. We're concentrating the energy and we're filling with wire. It's a great technique for welding up thin materials with 100% fusion on both sides. So this is an application we've done a lot of. This is journal bearings for rock bits. This is a metal-on-metal wear problem. And in a normal bearing, you would run a carburized steel against a Babbitt bearing. In the oil field, we run cobalt against silver because we spare no expense. So to apply this cobalt-based alloy to these parts, we're using plasma. Why? Because it's a great way to put down filler material, and you can use the powdered filler material. So we're running a Stellite 190, which is a high carbon Stellite 1 alloy. This is a CNC based system. And what's amazing about plasma is you can get near net shape. We were hitting plus or minus 7 thousandths of an inch on finished bead dimensions. And the reason that this is advantageous is these filler materials are typically $30 a pound, so you don't want to use any more than you have to, and they're also extremely hard, 58 Rockwell C, hard to machine. And so if you don't add any additional material, then you don't have to remove it during the final processing. So it was a great operation. We've got these running all over the world. This is definitely a good application for plasma because of the fact we're trying to put in dissimilar materials very precisely. The last application was a metal-on-metal wear problem. This one is metal on rock or ground engaging. So you need different filler materials. In this case, we're running composite filler materials. We're running a chrome nickel silicon boron matrix, which is high 50s Rockwell C. And we're running 60% tungsten carbide for the wear mechanism. So these teeth are cutting the oil wells. But the same approach can be used for extruder screws. It can be used for the ground engaging teeth on earth moving equipment. And once again, plasma is a great process. You simply can't get this material made into a wire and achieve the 60% or higher carbide counts. So a wonderful plasma application. You can see these are delicate parts and you need precise control of your weld. Definitely a good job for plasma. Plastic extrusion screws. I was surprised to find that the plastics industry uses exactly the same filler materials for metal-on-metal wear that we use in the oil field for metal-on-ground wear or ground engaging wear. And so the extruder screws that are operating in a plastic extrusion machine are non-lubricated metal-on-metal problems. So the bore of the extruder is constantly rubbing on the screw. And if there's any leakage, then you don't get full mold filling and such. So this is another good plasma application. In this case, it has to be absolutely crack-free. And so, as I was mentioning earlier, plasma seems to create crack-free welds much more readily than most of the other processes at reduced preheat. So what we're welding here is a long extruder screw up to 10 feet long. It'll expand almost an inch during the welding process. You have to compensate for all this. But a great application for plasma is the tungsten carbide overlay of extruder screws. So here's a close-up picture of an extruder screw. That's the part that's horizontal. You can see it has various different flight configurations on it. And then the torch is to the right, and we have the torch applying a chrome nickel silicon boron tungsten carbide overlay to this screw. The whole thing has to be preheated in this case to several hundred degrees Fahrenheit, so we're automatically compensating for thermal expansion. This is pretty much the standard technique in the industry for overlaying extruder screws. I wanted to include this application just to show you the other end of the spectrum. At the first one, we were welding 3/1000ths of an inch material. This is the other extreme. On the left, you'll see a very heavy part. That's I think it says 1,765 pounds. This is a tooth from a digger that's used in the oil sands up in Canada. The oil sands in Canada are so abrasive that parts tend to wear out within a matter of hours if they're not coated. And so it's worth spending some money and time and technology to coat these parts. But the sheer size of these parts means we can't weld them slowly. And plasma actually can work in the high deposition realm also. And so that's how we're coating these parts, is with a high current density torch on a CNC plasma welding system. So here's a detail of that high current density torch. This torch is operating at around 350 amps, but more importantly, it's operating at 10 kilograms or 22 pounds an hour deposition rate. This is huge. This is up in subarc range. And so we're able to put down huge volumes of metal, and you can see the weld off to the right. It's nearly 2 inches wide. Huge weld volumes, and interestingly, the powder capture rate is very high with these. We have such a large puddle, we have almost 100% powder utilization. So if people tell you that plasma is only good for fine, small parts, that's not the case. It really is a versatile process, anything from 3/1000ths of an inch joining all the way to these heavy parts with heavy welds at over 20 pounds an hour. One of the most common applications for plasma is in poppet valves for engines. Particularly after they phased out lead out of the fuel, we tended to have valve wear problems. And one way to overcome this is to coat the valve. So what you see here is a valve with the stems cut off, and it's partially welded, just to show you what we've done here. But that rim that actually seals against the seat inside the engine is coated with a high cobalt alloy to improve engine life. NASCAR has an interesting technique. A few years ago, they were lofting the tappets. That means the valves were floating. But as the team crew chiefs told me, you don't float, you don't win. But when the tappet landed back on these cams, it needed some place to land that was hard enough to take the blow. And so we were welding these camshafts with plasma. Traditionally, this had been done with TIG, but it's hard to automate TIG, and this was fully automatic, so we automated it with plasma. So on the left, you see 4 or 5 lobes that are plasma welded. On the right, you see a cross section. So again, this is a chrome nickel silicon boron, about 55 Rockwell C, and then they would grind the cam to shape after we had welded it. Made for a very long-lasting cam, but the technology is only practical for welding of race cams. My last example is of additive manufacturing. And we were early in the game. This was built maybe 15 years ago, and we did it with plasma. So what you see there is a machine that's capable of making a tube up to 20 feet long, all out of powdered material. And we're completely fusing this material with a plasma torch. Another good thing about plasma is you can see we have multiple hoppers. So as we were moving about this part, we'd actually change the chemistry on the fly with the multiple hoppers, and we could feed them through the same torch, which would be difficult to do with a wire feed system. Over on the right, you see a weld sample. This was titanium. We're getting over 150 KSI tensile strength. This is 15 years ago, so we were kind of on the leading edge of the additive manufacturing or the stereo printing or whatever you want to call the technology. But I feel like plasma might be one of the preferred welding processes for additive manufacturing because it's able to weld such a wide range of materials, all the way from aluminum, titanium, nickels, and steels. And you know, the industry's still in its infancy, but we had some good results way back then, and they're getting better now. Plasma welding is seldom used as a manual process, so we need to go into some of the control theory, both of how we control the welding power supply as well as how we control the motion of the torch. So I'm going to cover a few of these points today because it's part of the process when you're automating welding. We're going to talk about analog and digital control. We'll talk about closed loop versus open loop. Talk about starting sequence. With plasma, it's quite a complex starting sequence, and it's kind of good to know what goes on behind the scenes. So the first thing when we try to initiate the arc is we've probably already struck the pilot arc earlier. So typically on a plasma machine, the pilot arc is left running all through the day while the machine is up. And so the starting sequence on the pilot arc is first we turn on the pilot arc power supply. And once we see the open circuit voltage for the pilot arc power supply, then we initiate the arc with high frequency. So see, it's actually 2 power supplies used to make the pilot arc. And then we control that pilot arc as a function of current. Now we don't have to concern ourselves with voltage because the distance between the tungsten and the anode is always constant. So we simply let that run closed loop, monitoring the current alone. So that's how the pilot arc's running. And then when we start the arc, the main arc that transfers to the workpiece, it gets a little more interesting. On our systems, what we'll do is we'll double the pilot arc, which increases the amount of pilot arc coming out of the torch. It lengthens it and improves starting. We also increase the gas flow rate, and we turn on the main power supply. If we see open circuit voltage, that means the arc has not been established, but as soon as we see welding voltage, then the arc has been established. And so that's the sequence. That's just to get the arc going. And then we start at a low current. We don't want to start at full current. So we typically have a start current, which is maybe 10% of the target current. And then we slowly ramp up for a period of time up to the main current. And most of our welding systems, we capitalize on the advantage of pulsed welding. That means we have a high and a low pulse period. This reduces the overall heat input. And so as we're ramping up to peak current, we're actually pulsing all the way up. And then once we're finally at peak current, and then we continue to pulse probably at 2 or 3 hertz, that's 2 or 3 pulses per second. And typically our peak is twice as much as our background. So we reduce our main current by a factor of 2 on the background period, and we're pulsing back and forth just to reduce the whole overall heat input. When you're ready to weld, you actually start the powder feed in, and that we don't need to ramp that up typically. We just turn it on, and then we possibly delay to establish a puddle, and then we start traveling. Then we want to stop. It's a little more complicated. We stop the motion first, we continue to feed powder to fill the crater, and then we begin to ramp down. This is actually more critical in the startup sequence. We're ramping down over a set period of time, a programmable period of time, to a lower level to let the puddle solidify, freeze without any cracking. Then we finally shut off the main arc, and we leave the shield gas on to protect that puddle while it's still cooling, and leave the torch in place. So if you understand that starting sequence, welding sequence, and stopping sequence, you'll have a better handle on the process. And then the whole time we're doing error monitoring, and we're watching a lot of things. For example, most of these torches run not just a water chiller, not just water cooler, but a chiller, a refrigerated chiller. So we're monitoring this water flow rate. If we lose water flow rate, even for an instant, we shut down, because torches won't last but seconds without water. We're also monitoring the gas flow rate in real time. If the gas flow rate is not correct, we shut it down. Some of our more sophisticated systems, we're actually monitoring oxygen levels in our gas flow. We found that anything over about 18 parts per million oxygen can create weld defects in some of these critical, expensive parts. So it's not a hard matter if you have a computerized system to monitor oxygen in your shielding gas. And if we see high oxygen levels, we shut it down. At the same time, we're monitoring error conditions on all the welding machines. If we detect any of those, we shut the system down. So you've got constant error monitoring going on in the system. And you need to understand that so you can determine what errors shut your system down and what happened to your weld. And finally, we have the torch height monitor. Again, the torch height is extremely critical. I'm going to show you on the videos at the end of this class. But you don't directly control torch height because you don't really know where your part is. So what you do is you instead monitor the arc voltage, which is a function of arc length, and then you servo around that. So you need to understand the difference between analog and digital. Analog is an input or an output, which is a variable across a range. For example, you could have the gas pedal on a car, that's 0 to full throttle. You can have a light dimmer, which is off to full brightness. You can have welding current on a welder, which is amperage, which is between 0 and whatever the limit of your welder is. Typically in plasma, maybe 300 amps. So if you need to be able to control something specifically, you need analog control. And the alternative to this is digital control, which is an input or an output. That's either on or off. And examples are the horn on a car, or a light switch, or a gas flow solenoid. We're simply turning the gas on and off. On more sophisticated systems, though, for gas flow, we might use a mass flow controller, which is an analog version of a gas controller, and it allows us to control not just gas turning on and off, but the actual flow rate in real time. So some of the variables that we're going to talk about today are controlled analog, and some are controlled digital, but you need to know the difference. So let's talk about analog resolution. And so it's based on the number of bits that you're using. And a bit is either true or false, it's 1 or 0. And so if you have only 2 bits of analog resolution, then you have only 4 states. And in that case, you could create off, slow, medium, and fast. But if you have 64 bits, then it looks like you have 18.4 quadrillion states. Okay, that's more than we need for anything we're doing. And if you have 12 bits, that's 1 in 4,096. That's kind of typical in industry for tolerable analog resolution. Sometimes it's not good enough, but if you can control your amperage within 1/4000th, that's typically pretty good. Other things you might need better resolution, but I would look for a minimum of 12-bit analog resolution on anything you're doing for welding. Let's talk about open loop versus closed loop control. So a system which commands an output and then doesn't check it is open loop. So an example of that would be a light dimmer. You set the light dimmer on and you get what you get. If power diminishes, light diminishes, but it doesn't correct it automatically. Or a fixed throttle in the setting on your car. So if you put your accelerator halfway down, the car's going to go a certain speed on flat ground and go a little bit less up a hill, a little faster down a hill. But there's no control of the speed directly. You're controlling the throttle and nothing else. So that's open loop. And typical wire feed motors. On a wire feeder, they're pretty good. So what we'll do is we'll command a wire feed speed, and typically it won't vary by more than 15% or so. And in many systems, like your MIG welders, that's adequate. But in our world, if you're trying to achieve the precise tolerances that you typically want with plasma, what you're going to look for is closed loop control. So in closed loop control, a system monitors the variable and makes correction in real time. So float in a toilet, okay? As your toilet fills up, the valve slowly pinches off. Or cruise control in your car, you set it for 70 miles an hour. If it goes too fast, it'll reduce throttle. If it goes too slow, it'll increase throttle. Closed loop control. And then welding amperage on most welding machines is now closed loop through a Hall effect sensor. And that's good because you need to be able to control the amperage in real time, not just assume the machine's going to put out the right amperage. And then the example we're going to use later is torch height control. Because you don't directly control torch height, you control torch height through monitor of voltage. So if the voltage gets too high, you drive down. Too low, you drive up. So you need to understand the difference between open loop and closed loop, and you use closed loop everywhere you need it, and you don't use it where you don't, because it's unnecessary cost in some applications. So I'm going to talk about negative feedback and how it fits into a closed loop control. Negative feedback means as you get closer to your target, you reduce your output. And here's the example. Let's say we set the arc voltage equal to 10 volts, which is kind of a typical TIG welding number. And so we go through this decision-making tree, and we check the voltage in real time. Is the voltage greater than 10? If the answer is yes, then that means the torch is too far away. And you don't control the voltage, you control the position of the torch. You move the torch down, and then immediately afterwards, you check again. Is the voltage greater than 10? If it still is, you move the torch down. That's the concept of negative feedback. And if the torch is not greater than 10 volts, then the next thing you do is check, is it less than 10 volts? If the answer is yes, you move the torch up. That means the torch is too close to the workpiece and you have to move away. But you're controlling torch height based on arc voltage, negative feedback, and closed loop control. This is an essential feature in any TIG or plasma-based system that you're going to use in automation. So this is the list of variables that you must control when you're plasma welding. Yes, the list is long, but that's the good news. If you have control over these variables, you can truly optimize your results. You can weld materials as thin as 3/1000ths. You can control dilution very, very accurately in your part. You can control bead size, bead width, and bead depth. So after you understand each of these variables and learn to optimize them, frequently you seldom move any of these variables after you initially optimize them. You just make a few changes in amperage and powder feed rate. So it's not quite as daunting as you might suspect. Amperage is pretty much the heat input of your part. The more amps, the more power you're putting in the part. Voltage, this is your torch height. And you're going to see when I show you the videos that torch height is a very critical variable. So yes, we're controlling voltage, but we're more concerned with torch height. Travel speed. You can't weld faster than the weld will follow, as the old guys say. The weld will only travel as fast as it's willing to flow ahead, kind of like lava flowing down a hill. You can't rush it. So you have to control the travel speed. The powder feed rate, this is a critical variable, particularly if you're trying to create near net shape or do additive manufacturing. You need to know precisely what your weld volume is, because you don't want to underfill or overfill your joint. We have 3 gas flow rates. The plasma gas flow rate is a critical variable. We actually increase it on starting to improve starting, but then we bring it back down to reduce dilution. If you take it to an extreme, you'll actually cut through a part. But before you hit that extreme, you have blown your dilution rates and created huge dilution problems. Your gas shield flow rate, not a critical variable, but there are tolerances. Too little and we start to oxidize the part. Too much and we'll actually begin to disturb the puddle. We'll demonstrate this. And then powder flow rate. This one's kind of an interesting one. It's not a real critical variable if you have a vertical torch, but particularly when you're welding with long bore torches, you're using the powder gas to transport that powder through a tube in a horizontal state. So you're having to blow this material down there. So on the torch we're going to demo today, it's not too critical, but remember that that flow rate is important on bore torches. Torch height. Once again, that's more critical than arc voltage. We're more concerned with the actual height. I'm going to show you that, particularly with a powder torch, you have to have the powder impinge above the workpiece. We'll show you in a video. Gas composition. This is something I thoroughly enjoy playing with. What we found is, since you have 3 different gas supplies, you can change your gases up. We're running some reducing agents like up to 5% hydrogen in our shielding gas. And we can do some interesting stuff with gas composition. And your anode size. The whole point of plasma is to collimate the arc. And so if you have excessive anode sizes, you really don't collimate. But on the other hand, there's limitations. You can't have more amps than the size of your anode. So the very small anodes are limited to lower current settings. We're going to demonstrate this for you. And then waveforms. You saw on most of the videos I showed earlier, we're actually pulsing the arc. So you can get a lower overall heat input if you pulse high and low, and the average is actually less than what you would need if you ran a constant state. But now you've introduced 4 more variables. You have pulse peak, pulse background, peak duration, and background duration. That's if you're using a standard square wave, and it can get worse. We're going to show you some of that. And then oscillation variables. Once again, this is a key thing. You can't weld faster than the weld will follow. And so you have to consider the tip speed when you're oscillating, as well as oscillation width, frequency, on and on. So we're going to demonstrate all of this for you today and hopefully make you a better welder. So for those of you who have hung in with me through 51 slides, thank you very much. And if you're like me, you'd like to see some arcs run now. And so we're going to go out to the lab. Enough of this theory, let's do some practice. What I want to do is show you each of these variables we've discussed. I'm going to show you too little, too much, and just right, in my opinion. Of course, these numbers are very much a function of the materials you're using, the joints you're welding and such, but you need to get to a point where you can watch this arc and make an assessment of each of these variables and how to adjust them. I'm hoping that this will make you a better welding engineer or a better welder. Let's go to the lab. Before we get into this long list of process variables, I'd like to make a couple of points. First, although we have 12 different variables we're going to learn how to adjust, most of these you will set and forget. I'll try to be clear on which variables you'll actually be adjusting in production, but it's only a handful compared to the 12 we start out with. But initial setting of these variables is critical. That's why I felt like it was worth going through it. In the background, you're seeing some videos of some applications that I think are perfect for plasma. One of them is corrosion resistance. We're using hot wire and plasma to coat the inside of oil field equipment. Plasma does a great job, and the tungsten is shrouded, so we don't have any issues with tungsten contamination. Another one is metal-to-metal wear on a rock bit bearing. It's hard to beat plasma for cobalt overlay. The next one is ground engaging wear, where we're running a composite material with tungsten carbide and a chrome nickel silicon boron matrix for ground engaging wear, where the part actually rubs against the rock. All these are applications that I consider to be best suited to plasma. So let's start off with amperage or current. This is the variable that really controls heat input more than anything else. Right here, we're running at 100 amps. You can see a ripple with each pulse behind it. And we're going to now turn up to 120 amps. That's not a great deal more, but what you can see in the back of the puddle is we've lost the ripples with each pulse. But more importantly, you would see increased dilution in your part and diminished hardness. Now we're down to too low a amperage, and this is pretty obvious in the edge of the weld. You can tell it because it's not wetting and flowing. It's not working very well at all. You're not getting good fusion. And then we'll turn it back up. Now we're back at correct amperage. For this situation, it's 100 amps. It looks pretty good. This is a key variable you must learn to control. Now let's talk about arc voltage. This is another key variable. Here we have the voltage set properly. Now we're going to raise it up too high. It's pretty obvious. We're not getting good bonding. We're seeing some sparks. We've lost some of our shielding. Now let's go too low. Now we're crowding the arc. You're going to damage the torch. You're not making a good weld at all. This is something you have to set by eye, I'm afraid, because the voltage in the system is dependent upon your grounding and a number of other variables. So you might as well get used to setting this with your eyeball. Now we're back to good voltage. Let's talk about travel speed, another key variable that you will be having to adjust in production. Everything's set properly now, but once we speed it up, you see that the pulse rate is not keeping up, and neither is the weld. The weld's not following. So if you don't see that stack of dime ripples behind your arc, then you're probably traveling too fast. So now we're going to slow down too slow. Now what's happening here? Well, this could be an acceptable weld if you're looking for a thick weld buildup, but you may be getting excess dilution, and in taking this to extremes, you'll actually get lack of fusion because the weld rolls ahead of your arc. So let's put it back at good travel speed. That's more like what I like to see. You're staying ahead of the puddle and you're getting good fusion all around. Let's talk about filler metal deposition rate. In this case, we're using powder. Here, everything's set properly, and we're going to turn it up too high. That's still an acceptable weld. You may want that level of volume, but now we're going to turn it down, and it's pretty obvious when you don't have sufficient powder. You see the divot right where the arc is impinging in the workpiece? Tremendous dilution and an underfilled part. Let's put it back where it should be. We're going to lose the divot. We're going to start to build a good weld again. So there's a range that will work with powder feed rate, and you need to adjust this to match the dimensional requirements of your part. Let's talk about plasma gas flow rate, a critical variable. Once you set it, you seldom adjust it. So in this case, we're running 2 cubic feet per hour. It looks pretty good. And then let's turn it up. Now what you see here is we've actually made a divot. We've turned this into a cutting torch. If you were to analyze this part would have tremendous dilution and very low hardness. And now we're going to turn it down. That was up to 8 cubic feet per hour. We're going to turn it down. This is kind of dangerous because if you don't have sufficient flow rate, you can actually damage your torch with double arcing. So obviously too low, but that's 1 cubic feet per hour, and 2 is optimum. We're back to the optimal 2 cubic feet per hour rate, and we're making a good weld. Let's talk about shielding gas. This is one of the easier variables to set. Typically, you just follow the manufacturer's directions on the torch. Here we have it set properly. Now we're turning it up too high. What you see is the gas is actually distorting the arc. We're blowing the arc around. Now we're going to turn it down too low. And shielding gas job is to protect the part. You can see we're no longer protecting the part. We're starting to get oxidation, particularly along the edge of the weld. We're seeing sparklers flying out, so the powder is actually oxidizing and flying off the part. Now we're going back to where it should be, and we have a good weld. We're just following the manufacturer's suggested flow rate. Third and final gas flow rate, powder carrier gas. Here everything's set properly. Let's turn it up too high, and we actually distort the arc. We're blowing the arc off the part. We're not getting any fusion, so we're not getting any weld at all. Okay, now we're turning it back down, getting back to the optimum powder flow rate. And then we'll go the other extreme. We'll reduce it. Now, what this means is we're no longer going to be transporting powder through the torch to the part. So you start to see that we're not creating the weld volume that we're looking for. This is hard to differentiate with insufficient powder because that's how it manifests itself. So we'll go back to the correct setting. We get a good weld. This is a critical variable you have to set with your eye. So we're looking at the front of the weld because we want to discuss torch height. That's controlled by arc voltage, but what we're really trying to do is get those 2 powder columns you see entering from the top left and right to intersect immediately at the surface of the weld, right where the plasma column hits it. So everything's set properly in this video. Now let's go up. Now you see the 2 powder columns are intersecting above the workpiece. We're losing a lot of powder. We're making a bad weld. We're also losing some shielding gas. This is something you have to set with your eye. When you have it set properly, you have the maximum powder retention rate, which also creates more consistent weld volumes, more consistent weld size. So this really is a critical variable. And once you determine what the height should be, then you check the voltage. So let's go the other way now. We're going to crowd the arc, okay? Now at this point, the powder columns are hitting on outside of the weld. Same thing, we're losing too much powder. This is not set properly. We'll bring it back up to the way it's supposed to be. Let's talk about anode size. With a plasma torch, you need to match your current to your anode diameter. In this case, this is optimized for 120 amps. So here we have an oversized anode, so the diameter is too large. What we're doing here is we're not collimating the arc properly. You might as well TIG weld at this point. So if you ever see this, one of two problems. You have the wrong anode, or possibly your tungsten is too close to the end of the anode. Let's talk about gas composition. What you see here is a pure argon shielding gas. You see the edges of the welds are not wetting out. That's because we have nothing to reduce the oxides. There's no flux, there's no hydrogen. Here we change the gas composition. We're running a shielding gas with 5% hydrogen. The advantage of this is there's always oxides present in a weld, and you have to reduce them somehow or another because the melting point of an oxide is much higher than that of a base material. So you either reduce the oxides, that's get rid of the oxygen, or you throw too much heat at it to try to melt the oxides. The way we do it is we try to add a little bit of hydrogen, around 5% to the shielding gas, and you can see it does magic things. It allows that weld to wet and flow because we're reducing the oxides with a gas rather than heat. So this really isn't a variable that you would change in production. The reason we're showing you this video is if you're running hydrogen, I want you to be able to identify when you have a hydrogen mixer problem. What you'll see is the edges won't wet, the welds will be more oxidized, and you simply don't get good fusion. Here's some good pulse parameters. I'm going to keep it simple. We're going to keep the background at 50% of the pulse peak, and we're keeping the pulse, background, and peak periods equal. So all we have to do is change the frequency so we get the same number of pulses per inch, and they need to be closely spaced, but the weld must freeze on the background of each pulse. So now we've kept the travel speed the same, but we've slowed down the pulse frequency. We're still running a 50% background, but we're not getting enough pulses per inch. This is more like a series of spot welds than a real weld. So here we've kept the travel speed constant, but we drastically increased the pulse frequency. We're down at a 50 millisecond pulse peak. This is too high for this travel speed. In effect, the pulses all average out, and you might as well not pulse at all. You might use something like this, extremely high travel speeds, but it's inappropriate for what we're seeing here. Let's talk about oscillation. There's a number of parameters we have to adjust. What we're seeing here is the oscillation is either too slow for the travel speed, or the travel speed's too fast for the oscillation, or possibly the oscillation width is too wide and the weld can't keep up. So there's three ways that you could cause this kind of problem. One critical variable in oscillation is dwell time at the edge. You need to have the weld stay on each edge long enough to get good fusion, but here we've extended it too long. So we have so much dwell time on the edge that we're actually not getting any weld fill in the center. This is pretty easy to notice and easy to fix. You need to either decrease your dwell time or increase your frequency. Here's another example of oscillation frequency and travel speed not matching. We're moving so quickly with a low oscillation frequency that we end up, instead of having a good weld, we have more of a sawtooth pattern. This is easy to fix. You either increase the frequency of oscillation or slow down the travel speed. So this is the way we like to set oscillation. We balance the travel speed and the frequency so that we have the weld puddle remaining molten all the way across. We're getting good fusion on the edges. We don't get any of that sawtooth pattern, and we have enough dwell on the sides that we get a nice flat square looking weld. This is the way I would set oscillation. Now we have some bonus footage for you. One problem which is unique to powder welding with plasma is port plugging. I showed you the end of the torch. There's two small ports. That's where the powder comes out, enters the plasma column, and goes to your part. Well, if you have too many fines in your powder, or you're running too low arc voltage, or you simply run too long, you can end up with one or more of these ports plugging up. And so if you have a two-port torch and you lose one of them, you're going to have drastic underfill in your weld. This is something you have to watch constantly. Thanks for attending today's ARC Specialties Plasma University. I hope you benefited from the program. If you go to our website, we have a small quiz. If you pass it with an 80% or higher grade and contact our administrator, you'll receive a certificate of completion. I look forward to having you attend some of our other classes. We're going to do sub-arc, MIG, TIG, and most of the other welding processes in the near future. Thanks for attending today.